Okay, we're back. This is going to be Ellipse Numericals 1. And what we did in the past is I did the theory, and today we're going to do a couple of examples. Right? When I'm done with this example, I'm going to need to pause the video, clean the whiteboard, and come back. So you're going to see me walk off and come back, hopefully. Okay, first example is write the equation of the ellipse with foci 5, 1 and negative 1, 1, and length of the major axis is 8. So the first thing I like to do is plot those points. So I've got a foci here at negative 1, 1, 1, 2, 3, 4, 5, and another foci at 5, 1. Okay, it's going to be a little tough to do this by hand, but we'll try our best. Now, the major axis is 8, and by definition, the major axis is 2a, so therefore a would be 4. Now, since the foci are in this type of line, this is called a type 1 ellipse, and we can expect the major axis will have that kind of orientation. In most books, many books, that's known as a type 1 ellipse. So here we go. These are the foci, call it F1 and F2. And on the nice graph paper image that I've given you on the take-home part, you're going to have a nice grid here. It's going to come out better than what mine looks, I certainly hope. Okay. Also notice that that we can tell what the center is because it's going to lie on the line segment connecting the foci in the middle. So we want the midpoint of this segment, and the y value is obviously going to be 1. It's going to be at this height. 5 and negative 1 is 4. Half of 4 is 2. So the center of the ellipse will be right here. So I'm going to label that as C. And one of the things that we're going to need to do is we're going to need to keep track of all of our values. So let me make a list here. So I'm going to write down that the center is, we said, at 2, comma 1. Okay. And A is a 4. And, well, let's see. So we know the value of C. Okay. The value of C is the distance from the center to each of the foci. So the value of C is a 3. Okay. And notice that the other foci is 3 units to the left, and this foci is 3 units to the right. Maybe I shouldn't label this C because that's kind of confusing. Okay, C is the distance from the center to the foci, to each of the foci. Okay, so now in an ellipse, we're supposed to know we have the equation a squared equals b squared plus c squared. So it looks a little like the Pythagorean theorem, but it takes into account that the values of a, which are the endpoints of the major axis, are around here, and they are further away from the center than the foci. So a is greater than c, and in that case, we get this relationship. And if you go back to the derivation of the formula for the general form of the ellipse, then you will find that we use this as a substitution. We use a squared minus c squared. We put in b squared. I'm just turning this around a little bit. Okay, so let's work this out. A squared is 16. We're looking for b. Okay. C squared is, of course, 9. So b equals radical 7, plus or minus, actually. Okay, but we're just going to use the positive, and we're going to use the idea of the minus to go in the other direction. So we need to find a, b, and c. And keep in mind, we can also find the endpoints of the major axis very easily. That's the value of a. So we're going to go from the center and count 4 units. So this will take us to the point 1, 2, 6, 1. So we're going to have a vertex at 6, 1. And you go 4 units from the center in this direction, and you get negative 2, 1. Okay, so this we'll call vertex 1, and this we'll call vertex 2. So one of the things we're going to need to do when we do a problem like this is indicate the vertices. So the vertices are negative 2, 1 and 6, 1. And it doesn't matter whether you call this vertex 1 or 2. I'm just sticking with the notation here. Okay, so what I'm now going to do is use B. B is radical 7. So the length of the minor axis in length is 2b. So it's 2 radical 7. So what that means in English, I'm just going to count boxes, right? I'm going to start at the center. I'm going to go up radical 7 units. I'm going to go down radical 7 units. So radical 7 is about 2.6. So let me extend this just a wee bit. So this is a height of 1. So this is going to be 1 plus 2.6. Okay, 1 plus radical 7, I'm just going to write, and that's the y value, and the x value, of course, is the 2. So this is going to be one of the endpoints of my minor axis, and if I go down 1, 2, 2 points, so let's see, this is 1 unit, 2. If I go down about 2.6 units, I'm going to still have an x value of 2, but now I'm going to have a y value of 1 take away radical 7. Okay, so that's going to give us the other endpoint of our minor axis. So these are the endpoints of our major axis called the vertices, and these 2 points are the endpoints of the minor axis called endpoints of the minor axis. Okay, now what I'm going to do is I'm going to try and sketch this out. But one of the things when you try and sketch this out, well, let's write the general formula first. Right, it's x minus h quantity squared plus y minus k quantity squared over equals 1. Now, when the major axis is horizontal, the a squared goes with the x squared term. When the major axis is vertical, which is not the case because this is a little squished, then we would put the a squared here. All right, so this is our general form, and we have to come up with the formula. So this is the general form for a type 1 when the major axis is horizontal. So just put the numbers in. The actual center is 2, 1, right? So we have h is 2, k is 1, so we have x minus 2 quantity squared. We have y minus 1 quantity squared. Okay, and in standard form, this is a 1. Okay, so a squared, you can see 4 squared is 16. B squared, well, if I take b and square it, I get a 7. So this is the equation of that particular ellipse. One other thing we often do is the lattice rectum. Okay, so let me do that in a different color. We'll try green. We'll see if this works. So the lattice rectum is a line segment which is perpendicular to the major axis, okay? And we're going to get the length of this, and that's going to help us decide how squished or not this ellipse is. Okay, so the length of the lattice rectum, LR, length, we use absolute value, is 2b squared over a, and we did this in the theory part, the presentation. So we put the numbers in. Okay, so we got 2. B squared would be 7, and a would be 4. So when the smoke clears, you get, well, 14 over 4, or you can say 7 over 2, you get 3.5. Okay, so that would be the length of the lattice rectum. Okay, so if the length of the lattice rectum is 7/2, it's 3.5 units. I'm going to go up half that amount. So about 1, let's see, what's half of this? Half of this would be 7/4. I'm going to go up about 1 3/4 and down about 1 3/4 from the foci. So let's just try and approximate that. I'll put a green dot there. So this is one of the foci. I go up a full unit. This would be up another unit. I'm not going to quite go there. So approximately there. So I'm going up about 1 3/4 units. I'm going to go down about 1 3/4 units. And this is going to help me sketch my curve. The same thing here. Up 1 3/4 units approximately. Down 1 3/4 units approximately. So those would be the endpoints of my lattice rectums. And now I think the idea is make a sketch. This is the worst part for me because I'm off balance. So it's going to look something like this. Okay. Okay, so this is basically what the ellipse looks like. It's called the type 1 ellipse. And here's our center, which you're going to have to write down on the take-home part. I'm going to give you a little box to write down the coordinates. And you're going to have to specify, I believe, H and K. Right? So in this case, what do we find for H? H is a 2, K is a 1, and that's how we get the translations or the offsets here. Okay? And you're also going to have to make note of A and B. You're going to have to make note of the length of the major axis, length of the minor axis, stuff like that. Okay, so this answers the first one of the numericals I wanted to do. I'm now going to pause the video. We're going to do a second one, and then the next video I will go on with the type 2 ellipse, which is a type which is elongated vertically. So just wait a moment. I'm going to pause this. Okay, welcome back. I cleaned this up. On the internet, they recommend using a little bit of rubbing alcohol to clean the whiteboard. I used to use that, and I found out that Windex works better. So you spray it and wipe it down, and away we go. Okay, this also will turn out to be a type 1, where it's wider than it is high. However, we're not going to know that in the beginning, and one of the things I'm going to do is I'm going to show you how to tell that, okay? And this will be the type of problem that we'll be doing on the take-home. So I'm giving you an equation here. Doesn't look anything like it's in standard form, and part of what we're going to have to do is put it in standard form, and then from that we'll get the A, we'll get the B, we'll get the C, and we'll make our sketch, okay? And the word analyze here is a word that's used in most books. It's used in our textbook, and it basically says, say everything that you know about it. So ABC, center, foci, vertices, lattice rectum, make a sketch, standard form, etc. So I'm hoping that everything will fit on here, but here we go. Okay, first thing you want to recognize is you have an x squared and a y squared, so it's not a parabola, right? A parabola has just one of the variables squared. Second thing you want to realize is you got a 4 and a 9, that the coefficients of the squared terms are not the same. If they were the same, we'd expect a circle. However, this is going to be squished in one direction and not the other, so it's going to be an ellipse. And also we have a positive sign in between them. If you had a negative, you'd have a hyperbola, which we haven't done yet, which we'll do later on. Okay, so the idea here is typically complete the square. So what I'm going to do is, knowing that concept, I'm going to separate this into terms where we have an x and terms where we have a y. I may have to erase this depending how far this curve comes over later, but we'll see. Okay, so that's basically what I'm going to do. Now the tricky part is you don't have a coefficient of 1 there. So what you're going to do is you're going to pull out whatever is multiplying the x squared. And what that's going to do, if I factor out the 4, this is going to become an 8x. Okay? All right, so moving along, I'm going to do the same type of idea here. Factor out the 9, and you get y squared plus 4y plus something equals negative 64. Okay, so I think what I'm going to do is I'm just going to take this off and just a little arrow there to indicate that that goes there as well. Okay, so now the idea of completing the square, take this one, take half coefficient, that's 4, square root is 16. Whoops, okay. Half the coefficient's 2, square root is 4, and we're going to add those numbers to this side because I just added them on the left side. Okay, so I'm not going to put a 16 here. You got to be careful. It's 4 times 16, or 64. And I'm not going to add a 4 here because this is really 9 times 4, 136. So when the smoke clears, I have 4 times x plus 4 quantity squared plus 9 times y plus 2 the quantity squared equals, and when I add these guys up, these guys cancel, I just get a 36. Okay, so that's how we do it. Now, standard form, you want a 1 here. So whatever is here, you divide everything by that. So I'm going to divide each of the 3 terms by 36. So I get x plus 4 quantity squared, 4 over 36. All right, I get a 9. If I divide this by 36, I get y plus 2 quantity squared with a 4 here, and I get a 1. So this is my standard form, and that's what I've been shooting for. Okay, so once you got that in standard form, everything else sort of falls apart. Okay. Well, first off, you know this is your a squared because the greater value is the a squared. So the greater value goes with the x, so this is going to be horizontally squished or pressed, so it's going to be a type 1, and this is our b squared. Okay, and at this point, I think what I'm going to do is I'm going to erase this. You can always go back to it because this is a video. I'm going to make some room to do a little more work here. So let me get this off, get some room here. Okay, let's see how this is going. This doesn't work so badly. Okay, so I'm going to make some room, and I'm going to make a list of what I've found out so far. Okay, so just by looking at this, I know what my center is. It's negative 4, negative 2. Okay, I immediately know A is a 3. So that means that the length of my major axis is 2 times that of 6. Okay, I know that my B is a 2. So the length of my minor axis, 2 times 2 is 4. Okay, and at this point, I'm going to start plotting things and counting boxes, and that's really all it is. So now negative 4, negative 2, so this is my center, okay? And I know it's this type of ellipse, which most books call a type 1, but I'm not going to, that's not important, okay? The important is it's wider than it is high, okay? So since that's the center, the major axis is 3. I count 3 units to the right of the center, and that's one of my vertices. So let me make a list here. Let's make a list. Vertices. Okay. So I get negative 1, negative 2. Okay. 3 units in this direction. So this is a vertex. Let me put the V2 here. Okay, so this is V1, and V1 would be what? It would be 1 to the 7, negative 2. Negative 7, negative 2. Okay, So we already have a lot of pieces of information. Um, so this is kind of stuff you'd have to be able to fill in. Now, in order to get the length of the minor axis, I just double this. So that means I'm going to go up 2 from the center and down 2. So if the question asks what are the endpoints of the minor axis, then you can just, it would be -4, 0, and this one would be -4, -4. Okay, so I mean, you can memorize a formula for these things, but it's basically counting boxes. That's all. That's all it really is, counting boxes. So we start with the center, and then we count off in either direction. Okay, now the one thing we're missing here is C. We got A, we got B. Let's find C. We're supposed to know with an ellipse. This is the relationship between A squared, B squared, and C squared, because A is this length, and C we'll find is going to be shorter, so that's why the A squared's by itself. It's the greatest length. So A squared would be a 9, B squared is a 4, C squared, we'll work this out. C squared is a 5, so C is square root of 5. And when you do this on the take home, you're going to be expected to fill in the boxes, show a little bit of computation. It doesn't take much, okay? So 5 is about, radical 5 is about 2.2, I think. Okay, about. It's 2.236, I believe. I could be wrong, but about 2.236. So that means from the center, I'm going to count left and right that many boxes. So 2.2, let me do this in another color to make the foci stand out a little bit better. So this would be 3, so a little more than 2, a little more than 2. Okay, so those would be my foci, F1, F2, and let's write down the coordinates. Now, the x value of the center, well, let's see, where's my center? My center is -4, -2. So -4, I'm going to take away radical 5, and I'm going to add radical 5. So here's the way I would work that. I have -4 plus radical 5 and -4 minus radical 5. And that's how I affect the x. And the y is still -2. That's not going to change. So my two foci would have those coordinates. Okay? Now, what some books will do, in fact, I think on some of the other examples I did in class on Blackboard anyway, here's how I would write it. I'd write -4 plus or minus radical 5 comma -2. So the plus or minus just breaks down to these two situations. Okay, so either way. Okay, so let's see now. Have I boxed myself in? Almost. Okay, so these would be the coordinates of the foci, and I can't really put them into the diagram. Make too much of a mess. Okay, so the other thing I would like to get is the length of the lattice rectum. So let me make a little bit of space here. And the length of the lattice rectum is 2b squared over a. And don't forget, the purpose of that is to help us decide how much up, how much down to count to get the correct curvature spread. Okay, so b squared is how much? 4. So it's 2 times 4. A is a 3. So I get 8/3 is the length of the lattice rectum. So therefore, half of that is 4/3. I'm going to count up 4/3, about 1 1/3 unit up and 1 1/3 unit down, 1 1/3 up approximately from the foci, and 1 1/3 down. And then those points are going to help me draw the curve. And the last step, draw the curve. Oh, again, this is my worst. Okay. All right, so it's going to look a little bit like that, and it's pretty bad actually, but that's the idea. Okay, so this ends. These are the two examples I wanted to do on type 1 ellipses, numerical examples. And the next video is going to be two similar type of examples using the type 2, which is the vertical type. Okay, so I hope this makes some sense to you. If it doesn't, you can email me or just go over stuff again. Don't forget, the nice part about these videos is you can pause them, you can rewind them. I mean, you can watch a certain part again and again, focus in on it. You can change the screen size on your machine, I'm sure. And hopefully that will help. Okay, so this is up here, and see you back at the ranch.